Okay, so last time we discussed about like a system where we had n number of particles. Uh, okay, let me quickly take a look what we discussed last time. Then we will go to today's lecture. Okay. So basically last time we discussed about a system where we had n number. Is this PDF visible to you? Can anybody confirm?
Yes, sir.
Okay. So we discussed that we had n number of particles where there was some ith particle, and we represented the position vector of this ith particle as Ri vector, and we chose a point C. This was not among the masses itself, but it was just a point in space, and we call this point as the reference point. So C was the reference point. And then we defined some vectors like RC, Ri, and Ri with respect to C. So Ri with respect to C was just a vector of ith particle from C. If you are choosing this particle, then this is the vector. If you are choosing this particle, then this is the RIC. So then we saw that if we are able to apply the Newton's second law or the linear momentum balance equation for each of the point mass. Okay, so this Fi equal to MIAI, we applied for each of the particles. And also we saw that the that the net force on any particle, on any ith particle, basically is comprised of two components. One is Fi internal and one is Fi external. Fi internal corresponds to the force acting on this ith particle due to all other masses which we include in the system. And Fi external is a force which is acting on this ith particle, that is due to something which is outside this system, maybe gravitation, maybe electromagnetic in nature, something which is not included in this system itself. So basically any ith particle you choose, you can decompose the net force on that particle into two components. One is F internal and one is F external. Okay, then we also assume that sum of Fi internal, that is if you take the summation of all such forces. For example, you have ith particle and there is some internal force acting on it. Then you take this particle and there is some internal force acting on it. Similarly, there is internal force acting on this particle. If you take the summation of all those internal forces, you will see that the summation will be equal to 0. This is the direct consequence of action reaction pair. And then also we postulated that RIC cross Fi internal. That is, if we have Fi internal acting on this ith particle and we take the cross product of this vector, that is the position vector of ith particle with respect to C, with the internal force acting on that particle, and we take it for the whole system. That is, we also consider the force acting on this and cross this position vector with that internal force and take the summation over the whole system. We saw that this is also the 0. So when we took these two things into consideration, we saw that we used the Newton's second law for each of the particle, and then taking the sum of all the forces, we got the result that F external is something L dot, where L is nothing but the linear momentum of the system. And this linear momentum of the system is nothing but the summation of MIVI, where MIVI is the moment of any any ith particle. So you basically take the vector sum of all those momentas to get the momentum of the system. So basically this is saying that rate of change of the linear momentum of a system is f external. So you need not to take into consideration the internal forces. So you can write. So we got this equation. This is not taking into consideration the individual particles. So if you are you just saw what is the external force acting on the system. You have the linear momentum of whole system. So you can use this equation. Okay, then we also saw that this linear momentum is nothing but rate of change of total mass of the system times the position vector of the center of mass. Rg is the center of mass. When we utilized this thing, we got that F external is nothing but m times d2 Rg upon d2 dt2. So this is where we stopped last time. I think so. Yeah. So this is the equation. That is F external is m total of the system into acceleration of the center of mass. So now you need not to look at the individual forces acting on each of the particle. You need not to look into the acceleration of each of the particle. Rather, you have a bigger picture of the system. You just need to look at the net external force acting on the system, the total mass of the system, which is a scalar quantity, and the acceleration of a single point associated with the system, and that point is known as the center of mass, and you have to just look at the acceleration of that center of mass. Okay, a quick remark from this we can make. I am trying to open the whiteboard. If it opens, then okay. So you can see from this equation. So we have F external equal to rate of change of the angular momentum, or d by dt of L. So if the net external force is 0, so L dot is 0. We know the derivative of anything when it is equal to 0, that means the quantity itself is equal to some constant. So this is known as the law of conservation of momentum. So if you have the net external force acting on some n number of particles on a system, so basically if it is 0, then we can say the angular momentum associated with that system will be constant. And I have not assumed the system to be the rigid. So it can be anything, deformable system and other things. Okay, now let us go to today's lecture. So is it clear till now? Hello? Anybody having any question before I proceed to today's lecture? Yeah? Nobody have any question? Hello? Are you there?
No, sir.
So anybody having any question?
No, sir.
No? Mustafa?
No, sir.
Okay, so we will proceed. So today's talk is about angular momentum. So this is the most important with regards that the students usually make them, not only the students, most of the people usually make mistake when dealing with the angular momentum. So linear momentum to some extent is straightforward and you are well known with it and you apply it with without any error. But usually when you are trying to deal with this angular momentum and torque things, so here is where the students usually make the mistake. So I want you to follow each step very carefully so that you can solve your numerical problems efficiently. So basically, again, we will consider the same system. So we have first particle, second particle, third particle, and we have n number of particles. And again, let us assume that this is the ith particle, where Ri is the position vector of this ith particle, and Rc is the position vector of reference point. Again, I am emphasizing on this point that this C point is not something a particle. This is just a reference point. So I am taking the relative position vector of this ith particle with respect to this reference point, and I am calling that point as that vector as RIC. That is the position vector of ith particle with respect to C. And this bold arrow represents the force, net force acting on this ith particle. Remember, this net force is due to the internal force due to other particles, and it is also the force which this ith particle is experiencing from the external factors. So this Fi is the net force on ith particle. Now I am defining something like R, this vector, this relative position vector of ith particle with respect to C cross with this net force acting on that particle. And I can write this as Ri with respect to C. So this is Ri with respect to C, a little mistake here, cross Fi can be represented as, we know from the Newton's first law, if the net external force acting on some point mass is Fi, we can write it as mass times the acceleration, where Mi is the mass of this ith particle and Ai is the acceleration of this ith particle. As this is a point mass, we can directly use the Newton's second law. So I have replaced this Fi by MIAI. Now, this is for the for this ith particle. So we can do it for the whole system, and then we can take the sum. So basically, what I am trying to say, I don't know, this board is not working. Okay, board is still not working. Okay. So RIC cross Fi, you can write it this for this particle, but you can write this term for the whole number of these particles. And when you can write it for the whole number of particles, then you need to take the sum of all those terms. That is what I am doing here. Summation I running from 1 to n, Ri with respect to C, this term itself. So you put I equal to 1, so you are taking basically the first particle, then second, then third, and you are doing this for the whole system. But I already told you that this Fi, that is the net force on ith particle, it can be broken down into Fi internal, that is the internal force acting on ith particle, and external force acting on ith particle. And then I can replace this Fi by Fi internal plus Fi external. So when I do that, So when I do that, I substitute this Fi internal plus Fi external at this position, then take the cross product. So there will be RIC cross Fi internal, this term, plus RIC cross Fi external, and that is this term. Okay, but we have already assumed that RIC cross Fi internal is equal to 0. So here I can again show you. So basically, this is the net internal torque on any system is 0. This is the consequence which we were learning in the previous class. Okay, then so now there remains only one term, that is RIC cross Fi external. So RIC cross Fi external, summation from 110. So whenever I am omitting this this I equal to 110, so you need to look that it is basically the summation over whole system. So this is I equal to 1 from n, and this is also I equal to 1 from n. So RIC cross Fi external is equal to RIC cross MI AI. Is this clear up to this point? Yeah.
Yes, sir.
Is it clear?
Yes, sir.
थोड़ा जोर से बोले, मुझे तो लग रहा है कि नहीं समझ नहीं आ रहा है.
Yes, sir.
हाँ. Okay, others? Any question?
Sir, I have a question regarding the external forces.
Okay.
Sir, when car moves,
Yeah.
is the force generated by the engine external or internal for the cause of the motion of the car?
Okay. So if you are, so I have already told you this. First, the term internal and external, these are totally based on the definition of the system, how you define your system. My whiteboard is not working. I would like to draw something, but I don't know why it's not working. Oh, just a minute. I would, if it works. It would be better. So from your perspective, what should it be? External or internal?
Sir, if I take car whole as a system, then
Yeah.
then I think that it should be internal. And if I
Okay.
take road or earth and a car as both as a system, car and earth, then it is external. No.
You are taking both.
No.
Yeah.
Sir, when I take only car as a whole system,
Yeah.
then it is internal.
Yeah.
And when I take road as well as car as a whole system, then I think the force generated by this engine on the road is external, and by road on the car is also external.
Okay. Can anybody comment on this before I will say anything? Danish, Ikra, or Salik? Danish? Danish, are you there? Hello, Danish. Danish, Salik. Yeah, I am asking something. Danish? Hello? At least respond whether you are not able, you are busy, something. Shah Salik?
Yes, sir.
Yeah, are you there?
Yes, sir. Yes, sir.
Why are you not responding?
Sir, actually, you are just talking about Danish, so I was waiting for.
Okay, no, this is an open question. So Mustafa has raised a question. So I want you, if you have any comments on this question before
Sir,
I will.
I'm not getting this question. So please,
So
sir.
he is saying that the force generated by the engine. So we have a car. So obviously the engine is the main source of the force there. So he is saying that the force generated by the engine, whether it is internal or external.
Sir, sir, I think it's internal.
It is internal.
Hmm.
So then how the car moves? Because a car, if it is internal and we know that there can be no acceleration of center of mass without external force.
Mm-hmm.
So how is it possible that the car is running? And I think Mustafa has same question.
Sir, actually, maybe the road is giving the reaction forces. So
Yeah.
due to that reaction forces, the car moves,
Okay.
and that
So
reaction force is provided, but that is due to the wheels that provides
and
these reaction forces because they are in contact
oh
with the ground road.
yeah. So Mustafa, have you got the answer? And or I need to comment on
Sir, I got 80% of on.
80%. So basically, the force which is being generated by this engine, that is totally internal force. If you are obviously, we are taking the whole vehicle as the system. So the force generated by the vehicle itself, it is an internal force. But what happens is that when there are internal force like on the crank or on the piston, that force tries to rotate the crank and the crank then rotates the wheels. When wheels rotate, those wheels rub against the ground surface. And when they rub against the ground surface, they try to slip against it. And when there is slipping, you know that the frictional force acts. So there is a friction between the tire surface and the ground surface. And from the Newton's third law of motion, we know if there is a frictional force acting on the surface of the earth and it is due to the tire, so obviously there will be a frictional force which will be acting on the tire due to the earth, and that force will be in a direction opposite to the force being applied due to the tire on the earth. For example, if the tire is pushing or it is slipping and it is rotating when seen from the outside, that is from the side of the wheel. For example, if it is moving clockwise, so sorry, it is moving counterclockwise, so basically the wheel is pushing the surface of the earth due to its frictional force backwards. Obviously the frictional force on the tire should be in the forward direction, and due to that frictional force, that frictional force is applied due to the earth, so that is not the internal force, that is outside this system, and that is the external force, and that is the force which is responsible for the motion of the vehicle. I think Shah Salik answered it right. This was just a little bit addition to his question answer. Is it okay?
Yes, sir.
Okay, so let us proceed. So I was saying that this RIC cross FI internal, when you sum over whole the system, you take ith particle, you take its position vector from some reference point, and you consider the internal force on acting on the ith particle, you take the cross product, you sum over the whole system. This is zero. We have assumed this thing, and this is Also from it is also from the Newton's first law and third law that action and reaction torques are equal. So if any particle is applying a torque on any other particle, the opposite torque will be applied by that particle on that other particle in the opposite direction. And when you sum these up, they pairwise cancel out. This is that fact. And so this expression, that is summation RIC cross Fi, there will be only one term, that is RIC cross Fi external, and that is equal to RIC cross MI AI. Now this RIC cross Fi external, we call this as MCC. We call it as moment about the reference point C. It is very important. So there is no movement without any reference point. You cannot say that I am applying a torque of this thing. It has no sense. It makes no sense unless and until you do not mention that about which point you are applying this movement or you are applying this torque. So that is why we are defining this term, that is the summation of RIC cross Fi external, as the moment acting on the system, and it is equal, and this is the total external moment. See, there is no internal term. This is purely due to the external forces. So you need only to consider the external torques, not the internal ones. Okay. So no need of taking the internal force into the consideration. And see, like in previous, we saw that there was external summation of external force here. Here it is summation of torques and due to the external forces. And on the right hand side, there was some L dot. And we call that L as linear moment. Here also I am expecting on the right hand side something dot. That something dot I call as H with respect to C. See, when you are defining the moment about some reference point, you should also define the angular momentum with respect to some point. And this is known as the angular momentum. But this thing is not so simple. As it was for linear momentum, this is, you cannot define H with respect to C as you are defining the linear momentum. We will see what the problem, where the problem comes from. So what is this MC? This is nothing but Ri with respect to C cross Fi external. Okay, what is HC? We don't know. But what we know is that if we take the derivative of that HC, H with respect to C, we should get this thing. Is it clear? See, this is the equation we got. And now we are defining, this is the definition of MC. This is okay. And then we are defining something we don't know. And we are saying the derivative of that thing is equal to this right hand side. And we don't know what is this H with respect to C. So we need to define this H with respect to C. Okay. So let us think, but see, whatever we define it, this HC, the derivative should result in this form. So let us try to define this HC as Ri with respect to C cross Mi Vi with respect to C. So what is this Mi Vi? Can anybody tell me what is this Mi Vi? Vi with respect to C. This is linear momentum. Okay, so this is linear momentum. And you are taking the cross product of linear momentum. Okay. This whiteboard is not working. This is creating a problem. I don't know why it is not working. Okay. So now we are, so this is something which is linear momentum and you are taking R cross linear momentum. So you are basically doing one-to-one relation. You are saying that in previous thing we had F equal to linear momentum dot. And here I am taking R cross that force. So on that side, it should be R cross linear momentum. I think this is the intuition we are taking this thing. But we will see that there are problems with this thing. You cannot take this thing for all the cases. So let us take the derivative. So what we try to get is that when we take the derivative of this thing, so we should get this. This is the goal of our this section. So H with respect to C is summation of RIC cross MIVI. I know this is, see, this lecture is totally mathematical and previous one was also. So basically we are building some tools for more complicated systems so that we can solve them easily. Okay, the more tools you have, the easily you can solve the more complicated problems. Okay, so you have to bear this thing. Okay, so taking the derivative of this thing, this is the derivative of first cross second. So this is the chain rule or a product rule, not chain rule, product rule. So you are taking the derivative of u and v, that is derivative of u, that is first term cross second term we will write just as it is, plus first term cross the derivative of this thing, that is mivic dot. Now what is this RIC dot? That is the rate of change. This is the rate of change of RIC position vector, relative position vector of I with respect to C, with respect to the time. And what is VIC dot? It is d by dt of VIC. Okay. And RIC dot is nothing but VIC. So you can prove this thing. This is not a big thing to show. You can show, how you can show that RIC dot is VIC. Can anybody tell me or give any hint? I am saying that RIC dot is equal to VI with respect to C vector.
Sir, RIC can be written as RI minus RC. Then differentiate
Yeah,
both
then
sides.
differentiating that. Yeah, that is the thing. So has everyone got this point? Yeah. So we can write this RIC as RI minus RC. So this is from the definition, how we have defined RIC. Then you need to find the derivative. So take the derivative of RI, take the derivative of C, so that we will be getting VI minus VC. And VI minus VC is nothing but VIC. This is the definition of VIC. As we are defining RIC as RI minus RC, similarly, we are defining VIC as VI minus VC. Okay, similarly, you can do for this VIC dot. That is VI minus VC. Take the derivative of VI, take the derivative of VC, you will get AI and AC. AI minus AC is nothing but AI with respect to C. Okay. So we have taken the derivative of this thing. We have got this thing, and where this is this and this is this. Okay. So proceeding, we get summation of VIC. This is VIC cross MIVIC plus this is position vector RIC cross MI. This is nothing but AIC. So I am substituting it here, AIC. Okay. So I have written down for you what RIC is. This is RI minus RC. And taking the derivative, I get DRI upon DT minus DRIC. So this is VI minus VC and this is VIC. That is what I was talking about here. Okay, so now our equation is reduced to this. So HC dot is this thing. Okay. But what is this term? Can anybody tell me what is this term equal to? This term? This summation of VIC cross MI VIC. Yeah. Salik, Danish, Mustafa. Hello, Mustafa.
Sir.
What should be this term equal to?
Energy, sir, I think, sir, 1/2 of mv square.
How is this V square?
VIC into mv.
This is N2. This is multiplication.
This is
Sir,
actually,
maybe this is momentum, sir.
Momentum.
this is a
So what is this? This is the cross product. Are you getting this thing? This is not the simple
Sir,
product. This is
okay,
cross
okay, sir.
product.
Okay, sir.
Okay, so what will be equal to? Yeah. Ikra is there? Or she has left? Okay, she has left. Salik?
Yes, sir.
So VIC is some vector, isn't it?
Yes, sir.
And you
Cross
are
product.
taking the cross product of some scalar times that vector. So what should be this equal to?
It should be a vector.
So if we have a vector A and we are taking its cross product with itself, what should be the answer?
With itself. But it should
Yeah.
be unity.
It should be
Unity.
okay. Mustafa, if we have a vector V and we are taking the cross product of the vector with itself, so what should be the
kya, sir?
Just a minute. So we have a vector. Oh, what is happening? Okay. So we have a vector A and we have another vector. So we have vector A and we have another vector A and we are taking the cross product. What is the cross product equal?
Mod of A into mod of A into sine of theta. That is 0, sir, 0.
That is 0 because this theta is 0 between the two. So the cross product of two vectors is always a 0. Now
Sir,
take, so
V
now
cross.
take another thing. Take this vector. This is, for example, some V vector. And take another vector, some scalar C times V.
It's
So
also
what
0.
is this vector? This is also in this direction with some increased length because this is C times V. So if you take the cross product, these two vectors will be V, C, V sine of the angle between the two, isn't it? Some K vector. So what is the angle between these two vectors? It is again 0 because these two vectors are parallel. So just multiplying a scalar does not change its direction. So that can be seen. That is why I am saying VIC, this is some vector, and M times VIC, that is also another vector but pointing in the same direction. So the cross product of these two vectors will be equal to 0. So this term vanishes pairwise. You take any point, no matter what this I is, this term will always lead to a 0 vector. Is it clear now? For
Yes,
both
yes,
of
sir.
you?
Yes, sir. Yes, sir.
Okay. Okay, now the only thing is HC dot is now, we have only this term left. RIC cross MI AIC. RIC cross MI AIC. Okay. So what I will do now, HC dot is equal to RIC cross MI. This AI with respect to C, I will rewrite it as AI minus AC. Because we know that AI, so we know that AI with respect to C is nothing, AI minus AC. Okay, this is the definition of AIC. So when I write this, so we can write this H with respect to C dot equal to RIC cross MI AI minus AC. So what we were looking at, we were looking at that our, whatever we are defining this HC, the derivative of HC should be equal to this thing. This is what we were expecting. Because then only that equation which we got here, this thing, this equation will only hold if this derivative of this thing is summation of RIC cross MIAI. Okay, so whatever you are getting the derivative, it should be equal to summation of RIC cross MIAI. So RIC is here, RIC is here, cross MI, AI is here, AI is here. But there is another term AC. So we now try to vanish this term, that is AC term. If we somehow vanish this term, then only this will reduce to this thing. Are you getting my point? What I am trying to make?
yes, sir. Yes, sir.
Okay.
If AC
So
is 0,
सर एक बार रिपीट कीजिए सर यहाँ पर पॉइंट ही.
okay. So I am saying we define this HC here. See, I define this HC as this. Then I took the derivative of this thing and I got this result. This result I got by manipulating the things, by doing this and that. Ultimately, I got this. But previously we saw that the derivative of whatever angular moment or whatever you are, how you are defining this h, the derivative should be equal to this. Otherwise that thing will not hold good. But see here, it is this is not equal to this thing. There is this another term AC. So we need to vanish this term. How it will vanish? That is AC should be equal to 0, isn't it?
Yes, sir.
If it is 0, then this term vanishes and this dot will be equal to this thing what we are looking at. Okay. So the first thing is that AC should be equal to 0. What this mean AC should be equal to 0?
sir,
Yeah.
acceleration about
Yeah.
E0, sir.
Acceleration?
Acceleration,
What? Yeah.
Sir, it should be the acceleration on the same axis where we are just मतलब looking
No,
मतलब
what
जहाँ से हम लोग ले रहे हैं सर कंसिडर कर रहे हैं एक्सिस उस एक्सिस से
no,
0
what
होगा
is,
सर.
yeah, what is this AC? First tell me what is this AC? This is the acceleration of? Yeah, Danish?
sir,
Sir,
acceleration of
acceleration of point C.
particle at C.
Yeah, it is the acceleration of point C, not particle. There is no particle at C. This is the
Okay.
acceleration of this reference point C. I have not assumed this C as a stationary point. As the system moves, as the n particle moves here and there, this C can also move here and there. First it was here, then it could be here. So I have not taken this point as stationary point. But now I am saying that acceleration of C should be 0. Only then this equation can hold, and only then the definition we have defined, our angular momentum, will hold good. Okay. What this means is that the acceleration of this C point should be 0. It means that it should move in a straight line path with constant speed, or it should remain fixed.
Rest.
That is that are the only two conditions how the acceleration of c can be equal to 0. So the reference point which you are taking, against which you are defining your torque or the moment and the angular momentum, that point should be moving with constant velocity. Is it okay?
Clear.
Any confusion? Yeah, it is not that obvious. That is why I am insisting. If you have any confusion, you can let me know.
The C is a frame about which we are taking the linear momentum.
C is a
C means that C is any reference point about which we are taking the linear momentum acceleration.
not linear momentum, angular momentum.
Angular momentum, sorry sir, angular momentum.
Yeah,
So-
yeah. It is just a point. Yeah.
Can we say that sir it is a inertial, likewise we can we create sir inertial frame about C sir, and we can say that it is only true for inertial frame, that is when A is 0 or it is moving with constant velocity.
Yeah, yeah.
or
You can say that if we have a frame at whose no, see, there is a difference between a frame and a point.
point,
Okay,
yes.
there is a difference. For example, you can attach a frame to C, where C is moving with constant velocity, but the frame cannot be inertial. For example, the frame is rotating about C. Okay, but if you are attaching an inertial frame to C and the frame is moving, obviously moving with constant, yeah, then you can say this. But we have already defined this as a frame. Obviously, this is also an inertial frame. And we are then defining a point, reference point. At this point need not be stationary. I am again stressing on this point. This reference point need not be stationary point. Okay, so this can be moving. But now the way we have defined our angular momentum from this definition, this is the way we have defined our angular momentum. This imposes the constraint that AC must be equal to 0. And by this we mean that reference point can only move along a straight line, or it can be a stationary point. So you can have a stationary point and the system can be moving. These I particles, these can be moving, but till this C point is stationary, you can apply your angular moment balance equation easily and efficiently. Okay. So there will be no error. But is this the only only C point? Are these the only characteristics of the C point where we can define the angular momentum like this and we will get the correct equations? Or there are some other choices of C which we can take and the definition above results in a correct answer? So this is another question. So now let us go to it and see whether we have other options also. So again, looking at this system, that is, we have 1, 2nd, 3rd, 4th, and we have n number of particles. So in this n number of particles, we have chosen a reference point C. And we also know there is a special point with this system of particles that is known as center of mass, which is denoted by this capital G. Okay.
Okay,
Is
sir.
this Danish? Am I rushing? Sorry, Shas Salik.
Yes, sir.
Is it okay?
Yes, sir. Yes, sir.
Any confusion?
No, sir.
Okay.
Sir.
So yeah.
Sir,
Go
I
ahead.
think if C point coincides with the G, then there would
Yeah.
be another characteristic that it can follow the above. I
Okay.
think so.
So you mean that if we carefully choose our reference point as a
G.
point coinciding with G, then it
Yes,
should
sir.
hold. Okay. Let us look. That is, I think we will be looking for. So now we define this RIC That was the position vector of I with respect to C. Okay, this is RIC, and I can write this RIC as RG with respect to C and RI with respect to G. Is it okay? Can I write this? Is it correct?
Repeat, sir. It is little bit.
Okay. Can I write this vector as sum of this vector and this?
Yes, sir. Yes, sir.
Hmm?
This vector.
See, this is the triangle of vectors.
Yes,
Sum
sir.
of two is equal to the third but taken in opposite order. Oh, I have made a mistake here. Let me correct it before we will proceed. Just a I will show what mistake I have made. I think you didn't point it out, but
The vector should be, sir, opposite in direction, sir.
yeah, the vector should be now.
In opposite direction, then it is correct.
Okay, let me show you thing. See, I am saying that we have n number of particles, 1, 2, 3, so we don't need to mind about those. And we have some reference point here, which is C. And we have some ith particle among these n number of particles. I call this as ith particle. And there is a special point associated with this system, that is G, that is the center of mass. And then I am defining this vector as Ri with respect to C. This is what we have been doing for, I think, from the onset of this course. So this is the position vector of ith particle with respect to C. And then I can define this vector as position vector of G with respect to C. And similarly, I can define this vector as position vector of I with respect to G. Now I can write from the triangle of vectors, this vector, that is R G with respect to C, is equal to, sorry, just a minute. Okay, let me write it here. Not this thing. So R G with respect to C plus, so this vector plus this vector, that is Ri with respect to G, is equal to RIC. So we have this vector plus this vector is equal to the third vector taken in opposite order. This is the triangle of vector. So there was a mistake here. The only mistake is that I have drawn this arrow. It should be like this. This vector should be pointing this, not towards this. Otherwise, this is correct. Is there any confusion, or this is okay? This equation is right. Only thing you need to reverse this vector. This RIC is not in this direction. It is in the opposite direction. That is in this. Okay.
Okay, sir.
Okay. So I defined this. Okay, where is this? Okay. So now we have RIC as RGC plus RI with respect to G. But now let us rewrite this HC dot as RIC cross MI AIC. This is what we got from the previous section. So summation Ri with respect to C cross MI AI minus summation of RIC cross MI. So basically I have written this AI as AIC as AI minus AC. We previously. So what we need to do, so basically we have this term, what is originally there, which we don't want this thing. So this should be equal to 0. One choice was that we put this AC equal to 0, that we saw. The other choice is that this vector and this vector should be parallel. So RIC parallel to AC. If we have this condition, again this term will be vanished and we will be left out with this term only. So this is another choice. So the acceleration of the reference point, if it is equal to the position vector of ith particle with respect to the C, then also this will hold. Okay. Now let us go to the third condition. So now there is this term which needs to vanish. Are these the only two ways where how we can make this term vanish, or there are other possibilities? So we will write the summation of RIC cross MIC as, what is this RIC? This is RG with respect to C plus RI with respect to C. So RG with respect to C plus RI with respect to C cross MIAC. What I am trying to do, I am trying to eliminate this term. So I am writing this term as this, and then RGC cross MIAC plus summation of RIG MIAC. Okay. Now if I take the reference point equal to the G point, that is my reference point in itself is the center of mass. Okay. So what will happen? This is RG with respect to G. So what is RG with respect to G? Yeah,
Zero, sir.
0. Okay. So we have R G with respect to C equal to RG minus RC. But if C is equal to G, it means this will be equal to RG minus R. C is equal to G, RG. So it will be a 0 vector. Okay. So it is a 0 vector. So what will happen? That this term will vanish. Only this term will be left out. Okay. So our RIC cross MIAC is now RIG cross MIAG because C is G. C point is now G. Okay. Now I can write this RI with respect to G as RI minus RG cross MIAG. Now, okay. So RI MIAG. I multiply this first term by this thing. This is MIRI. And then I multiply RG with MI, that is MIRG, cross AG. I took this AG outside the summation because this is a constant. Is this AG constant? Yeah, Mustafa?
Yes, sir.
Previously in this setup, this AG is also in the summation. But in this setup, I have taken this AG outside the summation. The summation is only for this thing. I have taken AG outside. Is this constant? For the when you are doing the summation over the whole system, I am saying that AG is constant.
Yes, it is an
Yes.
expression of the center of the mass.
Yeah, and it is changing. I am not saying that the acceleration of center of mass is constant. I am not saying it. Just what I am saying is that it when you are taking the summation, so it is constant throughout the summation. For first particle, second particle, it doesn't vary when you are going from first particle to second particle because it is something which is related to the whole system and not to the individual particles.
Yes.
Okay. Or should I write? Okay, let me write it another way. Maybe that will help you. Okay. So what was the term? It was summation Ri minus Rg. Okay. So we had summation Ri minus Rg, and then it is Mi, and then it is Ag. Okay. There is a cross here. Huh? So then what I did, it is RI MI AG minus summation of MI RG cross MI AG. Okay. So This summation runs from 1 to n. So when you are doing this, for example, let us take the first term. So let's take the first term. What if I is equal to 1, what it will be? It will be, oh, what is going on? Okay. So I will write here. So, oh, what is this going on? I think there is some issue with this. So Ri, if I take I equal to 1, this will be R1 M1 cross Ag. And then it will be R2 M2 cross Ag. Then it will be R3 M3 cross Ag. So you can see this Ag term is not changing when you are doing the summation. So it is good to take this Ag outside the summation and take the summation of only Ri. Is now it clear? That is why I am taking
sir.
this Ag outside the summation. Now summation of Mi Ri. What is this equal to? Summation of Mi Ri. Yeah.
So it's also 0,
Can
sir.
No,
Sir,
how is
is
this?
sir, Mi is M total. Summation of Mi.
So we have so what is summation of MI RI?
Sir, it is angular velocity.
MI RI?
Yes, sir.
No, I think summation of MI RI upon M total. We defined this as RG. If you go to the previous lectures, you will see that we have defined this MI RI upon M total. This is actually the weighted mean of the position vectors. Okay, and that is what is the definition of RG. So summation of MI will be equal to M total
To RG vector. Yes.
Okay.
Sir.
Okay. So this is what I am writing here. MI is nothing but RG M total. Similarly, summation RG is constant. It is not going to change with this summation. I can take this out of this summation and then it will be summation of MI. So what is summation of MI? M1 plus M2 plus M3 plus M4, that is M total. Okay, so RG M total will be equal to 0. Okay, so we have thus been able to eliminate this term. That is the second term. So second term has eliminated. And this was our intention. So if we take this C point as G, this term will eliminate and we will be left out with this term. And that is what we need, because from this, the HC dot should be equal to this thing. So if you are defining your C equal to G, you will always get this equation. And your definition, like you are defining this, so you can define H C as this unless and until the C is G. Okay, is it now clear? Whenever you define angular momentum as I defined and take the C point equal to G, you will get the correct results. Okay, yeah, hello.
Yes, sir. Yes, sir.
Mustafa, okay. Salik,
Yes, sir.
are you getting my point?
Yes, sir. Yes, sir.
Okay. So we have this last page. Should I complete this one? This is the last and final for this. If you are willing, then I can complete this. I don't think this will take more than 5 or 6 or 7 minutes. But if you are willing. 5 or 6 minutes. If you give me more, I will complete this.
Yes, sir. If Salik Bhai is willing, then we can go.
Yeah, Salik.
Yes, sir. Yes, sir. Yes, sir. Go on, sir.
Okay. Okay. So now see, we have defined this H with respect to C as RIC cross MIVI. This is our definition, how we have defined the angular momentum. Okay. And then we saw that this RIC can be written as RG with respect to C plus RI with respect to C. And then this is MIVI, MI. This VIC can also be written as VI with respect to G plus VG with respect to C. Similarly, like we have done for this, you can also do for this. Just you have to differentiate this thing. When you differentiate this, you will get VIC. When you differentiate this, you will VI with respect to G plus VG with respect to C. This is nothing. So just differentiate this equation. Where is this equation? Why did we define that? Yeah, you need to differentiate this equation. You will get VIC equal to VGC plus VIG. Okay. So that is what I have written here. VIC is equal to VIG plus VGC. And now RG with respect to C cross MIVIG. So this is here. And see, Mi is constant. I can take it on this side, that side. It doesn't matter for the cross product. So this cross producted with this. Similarly, this cross producted with this. Similarly, this cross producted with this and this cross producted with this. These are the 4 terms we got from this when we do the multiplication. Okay. See, I am claiming that the only 2 non-zero terms from these 4 terms are these, which I have encircled. So this will be a non-zero term and this will be a non-zero. So only these 2 will be retained. These 2 are equal to 0. This term is 0. This term is 0. Okay. This is your like home assignment. This is not assignment. You can work this out. So I am saying that RGC cross VIG MI is 0. So you have to show this. This is 0. Okay. And I know you can do it. Similarly, you can also show RIG cross VGC MI is also equal to 0. So these 2 terms are 0. This I advise you to do when you go to home, you work out these 2 things, how this is equal to 0, how this, again, this is related to, like, you can write this as VI minus VG, you can write this as RG minus RC, then taking the summation, then using the definition of the center of mass. It is not a big problem. Okay, you do this. So there are only 2 terms left out, this and this. So our HC is RGC cross VGC summation of MI plus summation of RI with respect to GVI with respect to MI. So our HC will be equal to RGC cross VGC. What is the summation of MI? It is M total. So this is M total and this is VGC. Similar, this is R with respect to G and VI with respect to G and MI. So this is very important. Very important. This is the second most important equation you will be using. Okay. The first one was sum of the external forces is equal to the total mass times the acceleration of the center of mass. That was the first most important equation, and this is the second most important equation. Okay, so what this basically is, see, mass, this is the mass, total mass of the system. This is the velocity of the center of mass. So this is something that is mass times the velocity is something, it is the momentum associated with the center of mass. So we can say that it is the momentum of linear momentum of center of mass. And what is this? This is the position vector with respect to C. So basically you are taking you are calculating the angular momentum of what? Center of mass with respect to that reference point. So this is therefore known as angular momentum of center of mass, about that, obviously about that reference point. And what is this? This is mi vi with respect to g. So basically this is the linear momentum, but you are taking it with respect to the
Center of mass.
center of mass. So basically you are taking the angular momentum of each of the particles with respect to the center of mass. When you sum this up, you will find that it is the angular momentum of system relative or about the center of mass. So the way you have defined the angular momentum, that is h with respect to c above, that is actually nothing but the angular momentum of the center of mass with respect to that reference point plus the angular momentum of the system relative to the center of mass. So this is the most important, second most important relation or the equation which we will be using throughout the remaining part of the course. So is this clear? Are there any questions which I may like to answer? Yeah, any question?
Not yet, sir.
Not yet. Shah Salih?
No, sir. It's okay, sir. It's okay.
Okay, let me stop sharing this and then I will just. Okay, I have stopped the recording.